Today we are going to continue with our study on filters, digital filters. We are using the Fourier analysis to analyze the system look into the frequency domain, and then how to apply that to the input signal. So to perform the function as a filter out different components of a frequency, low frequency, high frequency, different components of my original signal. So before I start, let me share my Matlab example. I'm showing you one Matlab example here. So in Matlab, there are a lot of very useful functions that can help us do the frequency analysis, spectral analysis. And we don't need to memorize all these functions, but we need to know what's beneath it, under the hood. So again, the software evolves very fast. Some of the command, I don't remember. I don't even know that's coming new, the newest version. So we need to look into the help file or look for those spectral analysis, and in the process, and get to familiar with all these tools. And some of those are coming from the signal processing toolbox, from the optimization toolbox. So we will use that. Today we are going to look at, first, it's a very simple example, is to show you the power spectrum. So for the power spectrum, there's in Matlab a command code called periodogram. It's going to show you the power spectrum, which is capital X squared, capital X squared. And let's see if I can write here. Okay, it's capital X squared. Therefore, we don't have the phase information of the frequency domain signal. We only have the amplitude. Okay. So this example is very simple. I have a sampling period is 1000 Hertz. So T, this is the timestamps from 0 to 0.3 second, where the step size is 1/1000. So that's the period, is 1/1000. 1 millisecond is a step size. Signal is a cosine function with a frequency of 300 Hertz. So 2 pi t times 300 plus a random noise. So we have a noisy cosine function. The random noise is size of t. It's random n. It's a Gaussian distributed. Then on the figure, I'll plot this periodogram, which is x two-sided, and with 515 as my sample, and take the sampling frequency in it. All right, so this is the picture we have. It's oversampled, but we can see that it's from 0 to 1000. X-axis is just frequency in Hertz from 0 to 1000, and of course we know from 500 to 1000. That's the repetition, right? If you can move that to the other side of 0, that's negative frequency. And then we see here the frequency here is 300 Hertz. We got a peak. That's our cosine function. And all these rest, which is submerged with noise. These are the Gaussian noise, so we can see. And the entire power spectrum is normalized. So you're adding everything that's 1. So the y-axis is dB per Hertz, dB per Hertz. It's quite small, negative 30 dB, but it's per Hertz, negative 10 dB per Hertz. You're adding all together that give you a normalized energy. Okay, so that's one of the very interesting command in Matlab that we can see for the spectral analysis. Okay, so next part, I'm going to do a very simple filtering. This filter is an ideal filter. Basically, I'm using a box function, doing a low pass or high pass filter. So I had an example using a waveform, signal waveform, audio waveform, but it runs too long. So I am going to use a 2D FFT to work on an image. But all these things are very similar. FFT, I'm using FFT2, stands for a two-dimensional Fourier transform. So the input taking is an image. It's actually 2D. it just runs faster as my online demonstration here. So I'm taking an image, reading an image as beta football image. Figure 1, I'm going to show this original image A0. And then figure 2, I'm going to show a black and white image for A0. And because original A0 is color picture, so I have on each element, on each pixel, I have an element with a dimension of 3, RGB. So it's getting a little complicated. I just convert that to grayscaled. So on figure 2, it's going to show the grayscaled original image. Then I'm doing say a spectrum of A is doing an FFT2. That's a 2-dimensional FFT working on an image. Got this value, I'm taking the absolute value square. So I'm only going to take its spectrum, its density. And then the spectrum A is kind of in the size normalized, divided by the size of A, the first dimension, times size of A, the second dimension. So it's normalized spectrum A. Then also, we will have a FFT shift. It's the same as for one-dimensional FFT. FFT shift is just to shift the DC to the middle part, to the middle. Instead of from 0 all the way to Fs, now I'm from negative Fs over 2 to positive Fs over 2 over the entire window. Figure 3, I'm going to show show the spectrum. Now this spectrum, because the input is 2D, output is a value. So I'm going to show you a surface of this 3D image, The input is XY, output is my value. So figure 3 is the spectrum showing. And then what I'm doing here is I am taking FFT on the original signal, on the grayscale signal, say A frequency. And then here, this for loop is a very simple filtering. All I'm doing here is I'm checking the spectrum. If the spectrum on this particular pixel, P and Q, is larger than 50,000, then the frequency component on this pixel has become 50,000. So I'm simply cap that. In this filtering, you can put it 0, but here I want to show the image. I simply cap it. If it's larger than that, I just cap that. And then we do inverse Fourier transform. Again, that's 2D. Inverse Fourier transform on the processed frequency signal, A frequency, get a B. Now that will be translated back to the space domain, a function of X and Y. Then the last picture, figure 4, plot out the processed image. Okay, so let's see what it will give us. So that's what we have. So here, this is figure 1 is the original image. It's an original beta football, beta versus TCU. So this is the grayscale image. This is the surface. Surface doesn't show too much because we really have a very strong DC part. DC part, it's too strong. If you look at the scale, it's about 2, maybe it's 3 times 10 to the power 9. Compare all these rest. So it's very strong at the DC. So we don't see too much. And then the last image is somehow we filtered. Now remember, this is, I'm doing a cap. If my image has changed too much, meaning that the frequency is very high, and then I cap that. So the extremely high frequency, which is the sharp contrast of the image, it's been filtered out. It's been saturated. So we can see a very blurry, maybe a profile of those two players, but all these, the sharp contrast has been removed. Okay, let me change. So here, let me change a little bit. Let's say if all this, if it's greater than, I change that to 0. This may give us a lot of noise. We may not see clearly because everything is too sharp. Instead of keep it, I remove it to 0, to remove to nothing in the frequency. Let's see how this will give us. Okay, it's quite. This is I'm changing everything to 0. So you may not notice the difference, but it's quite doing the same thing. Instead of keep the high contrast to a fixed value of 50,000, I just remove them, make them 0. So this example in 2D is an example of a low pass filter, right? It's a low pass filter. The only low frequency component will go through this system. The high frequency component, which I used an if then command just to remove everything to 0. So you will see that I only have those little profile of those two players. So you can try different things. If you are doing a high pass filter and a low frequency, you can filter it out to see what it will give you. The second example is also working on image. Image is much faster for me to run demo here. And this example is working with a autocorrelation function. So autocorrelation function, you can write your own autocorrelation function. So I searched that, I found one in Matlab. It's just autocorrelation for 2D. I want to work with an image. So it's autocorrelation 2D here. I is my image. The original image is a random. It's just random, nothing. A random 501 times 501. That's a matrix 501 times 501. Each element is a Gaussian random number. Then I am doing an autocorrelation, two-dimensional autocorrelation on this image I. And a figure, plot, subplot the first picture, plot the image with the color of the image, I. Axis is equal height. So X and Y, they are the same size with a box on. Label X and label Y, that's the original image. And also showing me the color bar. So I know the range of those values. Now the value again, I'm plotting the image, but it's really a 3D plot, right? Because you'll take the x-axis, it's kind of x-axis is the xy of my image. The y-axis is the value of the pixel. In this case, it's a color. So I'm also using a color bar to indicate this value. On the second plot, what I'm going to do here is I am to do a spatial correlation. So I am plot A here. A is the autocorrelation of my original image I. So I'm plotting A here and make sure that's the same size. So I'm just move it to negative 250 to 250, make sure it's in the middle. And then title is spatial autocorrelation. On the second image, I'm reading an I.png. That's an interlocked BU. So reading that as image, doing the same thing, doing the autocorrelation, and to see what is 2D autocorrelation, the spatial autocorrelation will give us. And the BU picture doesn't show us too much. Actually, it's just a green sun. You will see a little bit, a very light in the background. Maybe you can see some. Let's run this program. Okay. So first, this is the first image. Remember, the first image is just completely random. So the original image here is completely random. Each pixel is a Gaussian random number. Then on the right is the spatial autocorrelation. So this gives you a 3D image. Only peak exists at the 0, 0. It's very light, but you can see this is at the 0, 0. It's a very light yellow, which means it's very high. It's very high. And all the other is close to 0. It's close to 0. So you're using the green color here. It's close to 0. And of course, you can try a 3D. If you're doing the surface, you will see one spike at the original 0, 0. The second image we have here is interlocked BU. I'm choosing the BU, it's green, and then the black as the background. So that's the special autocorrelation on the right. You can see a little bit here is on the top left and the bottom right. Maybe you got some spatial autocorrelation, and then showing you. And we can try different things. You can use some other pictures that may have a pattern. If the picture has a pattern, periodic pattern in space, and then you can see some meaningful large value in the spatial autocorrelation. All right. So let's look at how to do the filtering. Right. That's what we can do for the image for filtering. Last time we were talking about ideal filter. Ideal filter is we just doing a low pass filter, high pass filter, band pass filter. With the band of interest, we give it a 1, let it pass. The band out of the interest, we give it a 0. So you multiply by 0, you completely filter it out. And what we did is we see that ideal filter, we can use this H, capital H, using this formula. Now, out of the band of interest, that's all 0. Within the band of interest, it's a constant C. But somehow we will have this phase term here as well, because phase term, if you check with the amplitude or check with the power, it's just, this is gone. But we keep a phase term here, just in general. For an ideal case, this phase should satisfy a condition, and we call this a linear phase system. If the phase here is negative omega n naught, if it's a linear function of frequency omega, so n naught is a constant. Right? We using a group delay. Last time we were using a group delay to reveal this linearity. So the group delay is defined as the differential of the phase with respect to omega, and I take a negative sign here. So group delay is using this formula. Then if you're working on my original signal, this is ideal signal, which we have the phase is negative omega n, then this will give us n0. That's where it comes from. You know, where it give me in the formula, give me a negative sign, because the ideal case is, in this case, we have a negative sign here. Why do we like the negative sign here? Because it gives us a delay, right? It gives us a delay of hx and subtract n0. If you go through this ideal filter, the input go through this ideal filter, we will have a delay. It's a causal system. So you have a delay. I'm not going to get a signal in the future. I don't have that capability. I have a causal, a rational system. So you have a delay with a positive n naught. Therefore, we kind of put a negative sign here, and a positive sign here when you so define the group delay. And of course, go through the system, I also have a constant C. I also have a constant here. A linear phase is very good because it simply translates into a delay of my input signal. That is delay for all the input signal, whether n equal to 0, 1, 2, 3, everything, you just give me a delay. If it's not linear, this story may be a little complicated. You have to treat different signal with a different delay. That's the ideal filter. Ideal filter is in the frequency domain. We know ideal filter is a rectangular function. So in general, from F1 to F2, right? This is the highest frequency. If I say the highest frequency, that stands for Fs over 2, not crystal frequency, where Fs is the sampling frequency, 1 over Ts. That's how you digitize your signal. Ideal filter is a box function between the frequency of interest, that's 1, everything else is 0. Therefore, the impulse response is a sinc function. Rectangular function, you convert into the frequency domain. Excuse me, you convert back to the time domain. That's a sinc function. Right? So it will become a sinc in the frequency domain. Right? In the time domain, this is frequency domain. And this sinc function, actually, it's not around 0. Actually, it has some of the phase because my rectangular box is not from negative f to f. The sinc function is from f1 to f2. So a little bit scaling here. But overall, the shape is a sinc function. Now we know for a sinc function that it's not causal. Sinc function have a heavy tail on the negative time, and it is not absolute summable and therefore unstable. In this case, the Hn not absolutely summable by definition. We know it's not a stable system. So it's a not stable system. Neither is it a causal system. So it's difficult for me to implement. It's really an ideal case. It's not a practical case. How can we deal with that? Well, we want to design some practical digital filter. One important rule that we can use is we're looking in the Z domain, looking in the Z plane. If I'm looking at the Z plane, the system in the Z domain, we can discuss about its zero and oppose. The zero meaning that around this Z value, the output is, the system is really the output will be removed because the system is close to zero. The system is close. If it is around the pole for the Z domain, and then we know the output will be emphasized, will be amplified in the case. So that gives us a hint. Maybe I can use that to deal with the filter. So what I'm saying is here. So if we look at the Z plane, real part, imaginary part. If I got some pole here, that means if I have this is system, right? HZ. So I have something that's close here, point here, maybe point here. That this output, we have input XZ and output YZ, just abuse of those notation. Let me just write that. That's going through that. So we know it's a multiplication in the Z domain. If you have a pole here, this is a very large number. If you look into 3D, it's going to shoot up to a very large number, which means you emphasize the input signal around this point. Now, on the other hand, if let's say I have a zero here, HZ, meaning that this is just simply a zero. So if I got a point here, you go to the output, this will be nullified. The output will be close to zero. So that's indeed what we are doing a filtering. Now this is Z domain, right? The transformation domain is product. So we are doing a filtering. We let some components pass, we let other components removed. Now the Fourier transform is a special case of Z transform. Simply, we are looking at a unit circle. We are looking at a unit circle. So again, if you go along this unit circle from phase 0 to phase pi and back to phase 2 pi, and what I meant phase is this omega. Omega go from 0 to 2 pi. Actually, that's one circle here. And then if you're moving around to this position, this is my pole. Let's say I got a frequency here is 45 degree. Or in omega, that will be pi over 4. And then this filter give me amplification. The output is very large. Versus here at this point, it's 0. Therefore, if my omega is equal to pi, then the output will be removed. I don't have that. Now, what is omega equal to pi? That's the highest frequency I can have in my digital system, right? This is Fs over 2. That's pi, Fs over 2, which is this point right here. And if you really go from 0 all the way to, this is 2 pi, or which is Fs. So pi is really this point. That's the highest frequency. In this case, what I did is I have it's kind of a low pass filter. Low frequency will let it go, but high frequency is nullified. The location of poles and the zeros affects the frequency response characteristic of the system. And we will see an example. I think we did that example before, but this time we have a filtering frequency analysis we can look at in more detail. The basic principle underlying the pose zero placement method, how we do that? Well, we locate the pose near points of the unit circle corresponding to frequency to be emphasized, because the pose, you drop into the pole is kind of upwards. It's giving you a very large number. You emphasize the input signal. Locate zeros near the frequencies to be de-emphasized. And if you exactly land on the zero, then the output will be 0. Now for Z-plane, you can put the pose and the zeros anywhere in the Z-plane. But as we know, for a practical system, we are only looking at a unit circle. So in order to make sure that those zero in the pole will take effect in the frequency domain, we have to move those poles and zeros close to the unit circle. So all poles should be placed inside the unit circle in order for the filter to be stable. It should be close to the unit circle, but pole has a special character. I want to make sure my system is stable. Therefore, I need to put the poles inside the unit circle. However, zeros can be placed anywhere in the Z-plane. As we said, we'd rather put it on the unit circle, make it take a good effects. Complex zero in the pose. All complex zero in the pose must occur in complex conjugate pairs in order for the filter coefficients to be real. Remember that if my coefficients, A's and the B's, these coefficients, which are the A sub k's, B sub k's, and what are those? These are the coefficients of my filter HZ. If I'm putting into a rational format, right? We got a polynomial here, and the coefficient of the numerator are the B's, coefficient of denominator polynomial are the A's. If all these polynomials has real coefficients, then I need to have zero in the pose. Either they are real on the real axis, or if they are complex, they have to appear in complex conjugate pairs. Why do I need the filter coefficient to be real? Again, that's for implementation, because HZ, this is Y over X equals to a polynomial. Let's say just 1 subtract B1. And here, this is B0. Let me say this is 1 subtract A1 C to the power -1. Now, if you move that to here, that's Y subtract A1 Y C -1. And then move everything to B. So these are the coefficients. This is coefficient of this delay unit. Let me just look at this part. This part is a feedback. I'm going to feedback with a C to the power -1, taking the Yn in the time domain, and that gives me Yn -1. But you also want to give a gain to this feedback loop, for this feedback loop. So the gain is a real gain. So it's A1. For the pose zero placement method, the system function for my filter, capital H, as a function of Z, is a rational in this rational format. Usually we can pick up this B naught to select it such that the passband amplitude is 1. So when omega naught is in the passband of the filter, then the absolute value of H is equal to 1. That's how you choose the B naught. And suppose this is a proper rational function. So n is greater than equal to m. N is greater than equal to m. We have the denominator has the order not less than the order of numerator. Design low pass, high pass, and a band pass filter. Using low pass example as how we explain this. Design a low pass digital filter. We put a pose near the unit circle at points corresponding to low frequency. low frequency is here. This is DC, right? This is coming, you travel along the unit circle. That's my frequency, D, frequency DC, frequency pi here. So I want to put a pulse close to this point. And the zeros should be placed near or on the unit circle at points corresponding to the highest frequency, which is this point. I should put a zero here. This is pole. It's kind of ideal pole here. This is the ideal zero. So let's look at the low frequency, low pass filter. I put a pole here. That's a valid pole. It is within the unit circle, give me a stable system. And also I have just one pole, so it's a real pole. It's here. I can put two poles here. That's real poles. That's a valid pole because within the unit circle, give me a stable system. And I want to have a real coefficiented filter. Therefore, these two poles are conjugate pairs, complex conjugate pairs. And this is the example. I have three poles. So it's all close to the ideal case in the point here. Where do I put the zeros? So in this case, you can put a zero, which is at the origin, at the origin. You can also put a zero close to, actually zero is, it's okay to put exactly on the unit circle. So I'm putting here. Now put a zero at the original. All we did is that because remember the numerator is where the zero comes from. And I want to make sure that the order of numerator is smaller than the denominator. The simplest way I can do it, just become a constant, 1, or it's B0. And then you have here on the denominator, you got first order, maybe a second order. You got something here. I got two poles. But on the numerator, if we just give you a constant, make life easier, and then that implies you put a 0 on the origin. Of course, you can also put a 0 to the highest frequency, pi here, make sure that the high frequency component being nullified. All right, design a high pass filter. That's exactly opposite as the lower three pictures. For a simple low pass to high pass filter translation. Now, if I have already designed a low pass filter, or if you have given a low pass filter, I don't need to redesign everything. I can do a simple transformation and transform the low pass filter to the high pass filter. How can we do? Let's say the frequency translation of pi. So the high pass filter equals to take the low pass filter, but you change this variable, low pass filter omega, from omega to omega subtract pi. Well, very easy to picture that. You just simply remove all these zero in the poles. You rotate it pi. So whatever close to 0, phase 0, now will be close to phase pi. Whatever close to phase pi will be close to phase 0. Therefore, the entire characteristic of the poles and the zeros are exactly the opposite. And then you suddenly have a high pass filter. In the frequency domain, what we do, this is modulation of shift in frequency. That's modulation. So what we do in the time domain is high pass filter, is low pass filter modulate. That's multiplied by this e to the power j pi n. Now this exponential is very simple. E to the power j pi n, where n is the integer, that simply gives me -1 to the power n. It's either 1 or -1, depending on even or odd n. So an example is here. For example, if I have a low pass filter, it's given by this difference equation. It's given by this equation. A high pass filter can be easily derived. How to do that? All we know that I can simply putting a -1 to the power k here, a -1 to the power pi here. That's how we simply generate a high pass filter. Now, why can we do that? Well, it's coming from here. Also, you can discuss directly on the difference equation. All we need to do is I want to make the roots in this case is the 0 and the poles. The roots are shifted with omega subtract k. So you shifted the poles in the unit circle. You rotate pi. Rotate pi again. That means you do this, which means you putting a -1 to the power n, to the power k here on each term. And this part works for the poles, and this part works for the zeros. So it's very easy transformation from a low-pass filter to a high-pass filter. Before I go into a more complicated example, let me go back to example that I think we have seen that before. I hope this time we have a better understanding of this filter. What we did is when we do the Z transform, if you remember that when we do Z transform, we have designed a filter here. Okay, so for figure one here is I got a 0 on the origin, and a pole is right here, close to the unit circle, and it's close to DC because this is phase 0. This point is phase 0. Now, where does this come from? In figure 1 is B is 1, 0. Therefore, that's B naught is 1, B1 is 0. So the numerator is 1. It's really 1. Denominator is 1, negative 0.9. So it's 1 subtract 0.9 times z to the power -1. This is my HZ. Therefore, I have 0, which is on the origin, because you deform into a constant. You have pole, you check with the denominator, make sure the denominator is 0, and then we find that the pole is equal to 0.9. So the pole is here. And that's a very simple low-pass filter, because I want to emphasize the low frequency part. I want to emphasize when you travel on the unit circle around DC, because you got a pole nearby. So let's check with figure 2 here. There. This is the frequency Z. It shows you, actually it's giving you the frequency response, the magnitude response, and the phase response. Now this is the magnitude. The magnitude is indeed, that's a low-pass filter. When it's close to 0, I emphasize the signal. And it doesn't really remove everything frequency down to 0, because my 0 is putting on the origin. So it just it's going normal, right? But I emphasize on the DC part. The bottom picture, now then we can talk something about this now. What is that? That's the phase. That's the phase of my output H. So if you look at this Matlab code is I plot on the second subplot, I plot the angle of H, which is the phase, right? Phase of capital H. That gives me a nonlinear phase. Nonlinear phase. So that gives me something. This is a filter, very simple, just have one pole. However, it's not ideal. In a sense, it's not ideal in magnitude. It's not ideal in the phase term because phase is nonlinear. And I really like to have a linear phase, just one straight line. Figure 3 is similar thing. I'm just showing the whole frequency band, which this is from 0 to 2 pi. Make sure we are clear on this. 0 to pi, which is fs over 2. That's the highest frequency. From fs over 2 to fs from pi to 2 pi, this is the other side. It's a mirror. So you are going back to DC. So you can move this part to negative frequency side. So you can see a peak around DC. That's the bottom picture is the phase term, highly nonlinear. Just this curve, highly nonlinear. Okay, then we change a little bit. I change that. The second filter I have here is A is 1. A is 1. I don't have denominator. Therefore, this is a filter without any feedback. Also, this is a filter of finite impulse response. So what is this filter? It's a HZ equals to, now I don't have denominator. If you really want to write out denominator, it's 1. The numerator is 1 subtract, because a negative 1, z to the power, subtract 1, z to the power 1, 2, 3, 4, 5, 6, 7, 8, z to the power negative 8, right here. It's a FIR system, finite impulse response, because all we have here, I don't have feedback. So all you do is you take this input convolved with my filter, which the filter is just 2 parts. One is itself, it's a delta function. Another delta function is at the delta n subtract 8. You have a delay. So the entire impulse response has a finite support, meaning that over finite time, you got the positive, you get non-zero values. So it's FIR filter, easy to implement. All right, and then we're doing the same thing. We plot out this image on figure 4. So here is figure 4, as we said last time, when the numerator is 1 subtract z to the power negative a, you have 8 zeros. But these 8 zeros, because it's complex value, you solve a complex equation, z to the power 8 equal to 1, you got those 8 zeros that evenly spaced on the unit circle. And then the poles is deformed onto the origin because you don't have the denominator is a constant. So theoretically, I have same number of poles and the zeros. So I have 8 poles on origin. I have 8 zeros around on this unit circle. Then we can see here, this is my spectrum. The magnitude showing the response is like this. So I have exactly those 8 zeros right at those moments, right? 8 zeros. And the last thing I want you to see is, what about the phase? Well, the phase is actually linear. It's a straight line. Now you say, well, that's a turn off here. Well, that's just a pi over 2. Pi over 2, that's a wrap up. So if you stretch this onto a straight line, you can see it's going linear. And that's a good thing about the finite impulse response, because finite impulse response itself is a delay. It's a simple pure delay on the input signal. Therefore, the phase is linear.